Okay, in this video, we're going to be talking about rational functions. And a rational, if you remember, the root of rational is ratio. A rational function is any function of this form. F of x is equal to p of x over q of x, to where p of x and q of x are polynomial functions. So we're still dealing with our polynomial functions that we've been dealing with, except for now we're dealing with a quotient. You're dealing with the division of the two. Now, something else very important, q of x can never be 0. You cannot divide by 0, so you have to remember that as well. So there are some discontinuities here that we're going to be really focusing on. One of the simplest forms, or one of the simplest, and we've discussed this one already, is the reciprocal function, which is f of x equals 1 over x. And you can actually see a picture of that one here, to where it had the asymptote lines, to where it got closer, it approached it from each side and all that. The graph of the reciprocal function, again, is shown to the left. Okay, I've kind of already hit on this next part, an asymptote line, what it is. But let's go ahead and formally define it. An asymptote line is a line that a graph approaches. For example, in the graph to the right, the vertical asymptote is, and I drew it for you there, x equals -3. Remember that vertical lines have equations of x equals, and the horizontal asymptote is y equals 1. And again, I drew that one as well. Notice that these lines, my graph approaches, gets closer and closer and closer to, but they never cross them. Okay, a hole. A hole is removable discontinuity, which we've already talked about, or a break in the graph. Here you see a hole in this graph. If p of x and q of x have a common factor, now this is already telling us how we know if something has a hole. If it has a common factor at x equals a, then there will be a hole in the graph. Here's an example. The function of f of x equals x minus 2 over x minus 2 times x minus 1 has a hole at x equals 2. Now, how'd you know that? If there is a common factor in p of x and q of x, again, which is what this is saying, if p of x and q of x have a common factor, x minus a, then there's going to be holes at x equals positive a. So this has a hole at 2, which you can see actually over here in the graph. Now, why do we call this removable discontinuity? Well, now hopefully it's very evident. That's why they call it removable discontinuity, because you could actually remove that discontinuity. And if you were to graph just this without the x minus 2's, it'd be this exact same identical graph with no hole in it. Okay, graphing rational functions. We're going to rewrite the function in factors form. We're going to simplify. Step number 2, find the x-intercepts. Step number 3, find the y-intercepts. And we remember how to find x and y-intercepts. We plug in 0 for y, and we plug in 0 for x to find those two intercepts. Number 4, we're going to find our vertical asymptotes by finding the zeros of q of x. Number 5, we're going to find the horizontal asymptotes by using the rules below. Okay, here's how we know where our horizontal asymptotes are. We look at the degrees of p and the degrees of q. If the top degree, remember p is on top, we're doing p over q. If the degree of the top is greater than the degree of the bottom, then there will be no horizontal asymptote. Now, in this case, we will have what's called an oblique asymptote, and we'll discuss that more later. If the degree of p is less than the degree of q, then you'll have a horizontal asymptote at the x-axis, also known as far as the equation goes, y equals 0. That's going to be your horizontal asymptote. It will approach the x-axis. And finally, if the degrees are the same, then your horizontal asymptote will be y equals the leading coefficient of p of q, or excuse me, of p, over the leading coefficient of Q. We're going to look at our leading coefficients. And then step number 6 to graphing, we're going to identify any holes by looking for common factors. And we can actually do that a little bit earlier. We could do that in one of the first steps if we'd like. Okay, number 1. This one is already in factored form. The bottom's factored, the top's factored. So let's go ahead and find some intercepts. Again, if you don't remember, to find an x-intercept, we plug in 0 for y. To find a y-intercept, we plug in 0 for x. So let's find those two intercepts. So let's start out with our x-intercept. We're going to plug in 0 for y. So it gives you x plus 1 over x minus 5 is equal to 0. Now think about this. How in the world can we solve this? What methods can we use? Well, here's the easy way. In order to solve a fraction equal to 0, there's only one way for a fraction to be 0. If you have x over 3 equals 0, how can a fraction be 0? Only if the top is 0. So here x would have to be 0. What about the bottom? Can the bottom be 0? Never. So therefore, anytime you have a fraction equal to 0, all you have to worry about is what makes the top equal to 0. So your x-intercept here is going to be -1. So you have an x-intercept at -1, 0. Your y-intercept, in order to find a y-intercept, let me erase all this. You have to plug in 0 for x. So your y-intercept would be y equals 0 plus 1 over 0 minus 5. You have a y-intercept at -1/5. That's going to be 0, -1/5. We can go ahead and plot those 2 points. Here's your x-intercept, and your y-intercept is going to be somewhere right in there. Next up, let's find any vertical asymptotes. And while I'm looking for vertical asymptotes, I like to, in this same step, go ahead and find holes. Now, here's what you're going to do. Anywhere the function is undefined, which is anywhere the bottom is equal to 0, you might have a vertical asymptote or you might have a hole. And you can go back and look at our instruction to figure out which is which. But if something x minus 5 is a factor of both the bottom and the top, then you have a hole. If it's a factor of the bottom, then you're going to have a vertical asymptote here. So at x minus 5, x here obviously cannot equal 5 because that would be division by 0. So what happens at x equals 5? That's where you have a vertical asymptote. So let's come over here. At x equals 5, we have a vertical asymptote. Let's go ahead and put that on our graph. And this function will have no holes because there's nothing that's a factor of both the top and bottom. Finally, let's find our horizontal asymptote. Okay, your horizontal asymptotes, let's scroll back up and remind you. You have to look at the degree. If the degree of top is bigger, there's not going to be one. If the degree of the top is smaller than the degree of the bottom, then y equals 0. If the degrees are the same, then you're going to look at the leading coefficients. In this case, the top degree is 1, the bottom degree is 1. So we're going to look at our leading coefficient of the top and the leading coefficient of the bottom. And the leading coefficient, if you don't remember, is the coefficient of the highest power of x, which is x to the first and x to the first on top and bottom. So your leading coefficients here, your horizontal asymptote would be at y equals, leading coefficient on top is 1, leading coefficient on bottom is 1. So at y equals 1, you're going to have a horizontal asymptote. So let's go ahead and graph it as well. And let me finish out all of our information over here. Let's see, the domain, the only thing that x cannot be was 5, so x could not be 5. It could be anything else. The range, x can be, or excuse me, your y values are going to be anything except for, well, we'll wait about the range till after we get the graph. But we know that our horizontal asymptote here is going to be excluded from our range. Holes, there were none. So now, as far as actually drawing this graph, you can plug in a few more points, do you a t-table to get a few more points on your graph, plot those points, and then we'll see what the graph looks like. Let's see. I'm going to plug in maybe 1, 2, 3, 4 to see what happens here, and then maybe 5 is undefined, so 6 and 7. Let's plug those values in and see what we get. Okay, so here I've plugged those values in, I've plotted my points, and because of those asymptote lines, I can now connect my dots and we see exactly what my graph looks like. So here you see where I plugged in the points, I plotted the points, I connected my dots, I follow the asymptote lines because I know my graph approached them, and here's what I get for a graph. Now the range, notice my graph goes down forever, up forever, but there is a break in the graph right here at this y value, so my y value will never be 1 because it follows that asymptote line, and there you see that graph. Number 2. First thing, let's look at our domain. I see there that x cannot be -2 because at -2 I would have division by 0. So at -2, once again, one of two things are going to happen. Either you're going to have a vertical asymptote or you're going to have a hole. So to determine that, let's factor this completely. The top I can factor a 3 out of, and you're left with x plus 1. On bottom I have an x plus 2. Again, if a factor is present on top and bottom, there is a hole there. I have an x plus 2 on bottom, but I do not have one on top, so there are no holes. However, the other thing, if you have a factor on bottom but not on top, then you're going to have a vertical asymptote where that's going to be 0. So at that x equals -2, that's going to be a vertical asymptote. So we can go ahead and plot that on our graph. Okay, we'll go ahead and find our intercepts. In order to find an x-intercept, we're going to plug in 0 for y. So we're going to take out the y and put in 0, or we can just come over here and say equals 0. Again, the only way that a fraction can equal 0 is if the top is equal to 0. So therefore, divide by 3, whatever you need to do, but x is equal to -1. That's going to be your x-intercept. So x-intercept at -1, 0, and you can go ahead and plot that on your graph. So there's your x-intercept. Your y-intercept occurs when you plug in 0 for your x's. So to find our y-intercept, I'm going to plug in a 0 here and here. And that gives me on top 3 times 1, which is 3. And on bottom, it gives me 0 plus 2, which is 2. So my y-intercept is 0, 3 halves, or 1.5. So here is my y-intercept. Let's find our horizontal asymptotes. And this is a lot of information, so we really need to focus on this lesson and make sure we understand how to find each of these. Find the horizontal asymptote, we look at the degrees. If the degree of the top and the degree of the bottom are the same, which in this case is x to the first and x to the first, it is, we look at our leading coefficients. Leading coefficient on top is 3, the leading coefficient on bottom is 1. So therefore 3 over 1, y equals 3 over 1, or y equals 3 is our horizontal asymptote. Let's go ahead and graph that. And there you see that. And from there, if we have just a couple of points, then we can get a pretty good looking graph. When we plug in, let's do a small table of values just to get a few. Let's plug in maybe a 1 just to see. We already know the more you do it, the more you're going to know what this is going to look like. But I do want to know what my graph looks like over to the left of this asymptote line. So let's plug in -3 and maybe -4 and see what we get. And there are my values. So when I plugged in 1, I got 2. When I plugged in -3, 1, 2, 3, I got 1, 2, 3, 4, 5, 6. When I plugged in -4, let's see, 1, 2, 3, 4, I got 4.5. 1, 2, 3, 4 and a half. And that's plenty of points because I know that my graph is going to follow my asymptote line. So here it's going to do something like this. Then it's going to follow it down here. And then up here, it's going to do the same thing, and it's going to look just like my reciprocal function. These, again, are simply derivations. They're kind of changes or transformations of those parent functions, 1 over x. So it's going to look a lot like those in most cases. Now, some of them will be a little bit more advanced, but that's your graph. Your range values are going to be all values except for 3 there. And you could write that as all values from -infinity up to 3 and from 3 to infinity. Either way will be fine. Number 3, let's first off factor. Factor the top, 2 sets of parentheses, x times x, adds, multiplies would be a -5 and a +3. So there we go. On bottom you have an x plus 3. Let me clean that up. So the only thing not in your domain, you cannot divide by 0, so x cannot be -3. So the question now is, do I have a hole there or do I have a vertical asymptote there? Notice you have a removable discontinuity there. X plus 3 on top and x plus 3 on bottom. That means that there is a hole at x equals negative 3. There is no other discontinuity, so you will have no vertical asymptote. So what we can do at negative 3 on our graph, just make sure to remember that we are going to have a hole there. Okay. Now from there, if you would like to, you can actually now remove this discontinuity. And you can find out the exact, once you do that, let's get into this habit. Let's go ahead and do this. So your function is now y equals x minus 5, but you have a hole at negative 3. Well, where exactly is the negative 3? You can plug that negative 3 into this, and you can find exactly where your hole is going to be. Negative 3 minus 5, or f of negative 3, is negative 8. So therefore, that hole is going to be located at negative 3, negative 8. So let's go over here at negative 3, negative 8. 1, 2, 3, 1, 2, 3, 5, 6, 7, 8. And let's put a hole right there. And from there, the easy way, let's go ahead and find our x and y intercepts, but I'll show you the easy way now of doing this. To find the x and y intercepts, again, you don't have to, once you remove that discontinuity, you don't have to use this anymore. We can now use this, and just remember it's going to have a hole in it. So our x-intercept, to find our x-intercept, we plug in for 0 for y. So I have x minus 5 is 0, so I have x-intercept at 5. So 5, 0. I have a y-intercept. We're going to plug in 0 for x. So that's going to be y equals 0 minus 5, which is negative 5. So 0 comma negative 5. So I have an x-intercept at 5, 0, 1, 2, 3, 4, 5. A y-intercept at 1, 2, 3, 4, negative 5. Now, what does this graph actually look like? Guys, this is a line. This is in y equals mx plus b form. Your y-intercept's negative 5, your slope is 1. Here is your graph. This graph is a simple line. The only difference is you have a hole right here in your graph, but the rest of it is linear. So there's your graph, and that graph does go forever in this direction as well. It just has a hole. It has that removable discontinuity. So let's finish all of our stuff over here. My range, my y value will never be negative 8, but that's the only place that my y will not be equal. Horizontal asymptotes, I had none because it ended up being x squared on top, x on bottom. So anytime the degree on top is greater, there's not going to be a horizontal asymptote either. Okay, the next one. Let's always factor first. You've got x plus 2 times x minus 2. That's conjugates, difference of squares, factors into conjugates. You have an x minus 2 on bottom. So you have the exact same scenario. You have an x minus 2 on top and an x minus 2 on bottom. So that means that x cannot be 2. Well, what happens at 2? Is it a vertical asymptote or a hole? If there's a factor on top and bottom, it's a hole. So you're going to have a hole at x equals 2. And to find out exactly where it's going to be, let's clean this up and change your function to y equals x plus 2. And you can plug now that in to find out where your hole is going to be. F of 2 is equal to 2 plus 2, which is 4. So therefore, your hole is going to be located at 2, 4. So let's go to 2, 4, and let's draw a hole. So there's the hole in your graph. Now, again, there's your function. You can find your x and y intercept if you'd like. To find an x-intercept, plug in 0 for y, and you have, let's write it down. Find an x-intercept, you have x plus 2 is equal to 0. So that's going to be negative 2 is your x-intercept. So that's going to be negative 2, 0. You'll have a y-intercept where you plug in 0 for x. So you're going to have y equals 0 plus 2, which is going to be 2. So at 0, 2, you have a y-intercept, and you can plot those. Negative 2, 0, there's your x-intercept. Here's your y-intercept. You will have no vertical asymptotes here because, again, there's no other discontinuity on bottom. Horizontal asymptotes, the degree of the top is greater than the degree of the bottom, so there will be no horizontal asymptotes. And again, from here on out, honestly, you can just graph it like we normally would. y equals mx plus b. It's a y-intercept of 2, a slope of 1. So just connect your dots or draw your points here. Now let's connect our dots. And again, this is a linear function with a hole in it. So pretty much this is the graph of y equals x plus 2 with a hole at 2, 4. So your range will be everything except for 4. The next one, you have an x minus 3 on top. And after you factor, you have two sets of parentheses, x times x, adds multiplies would be a negative 3 and a negative 2. So we have another hole in this graph. However, here we have 2 points of discontinuity. X can't be 3 or X can't be 2. So our domain here, X cannot be 2 or 3. Now the question is, what happens there? Do I have a vertical asymptote there or do I have a hole there? If something's a factor of top and bottom like X minus 3 is, then I have a hole. So let's take, and at X equals 3, let's put that I have a hole. But let's go ahead and clean that up. Let's mark that out, and instead of graphing that, let's now graph nothing's left on top, and you have an x minus 2 on bottom. Here's my new function. I've removed that discontinuity. I'm just going to remember that I do have a hole there. Okay, the other point of discontinuity, the x minus 2, since x minus 2 is not a factor of top and bottom, then you will have a vertical asymptote at that discontinuity. So at x equals 2, you will have a vertical asymptote. So let's go ahead and graph that. And there you see it. Let's go ahead and find our x and y intercepts. Whoops. Let me erase that. Let's find our x and y intercepts. Again, to find an x-intercept, plug in 0 for y. To find a y-intercept, plug in 0 for x. So your x-intercept, plug in 0 for y. So 0 equals 1 over x minus 2. So that looks a little odd. How can 1 over x minus 2 equal 0? It can't. So you're not going to have an x-intercept here. And next, our y-intercept. We'll talk about in a second why you're not going to have an x-intercept. To find a y-intercept, we're going to plug in 0 for x. So I have y equals 1 over negative 2 or negative 1/2. So my y-intercept is going to be at 0, comma, negative 1/2. Again, I had no x-intercept. So let's plot our 0, negative 1/2. It's going to be right in there. Okay, let's find our horizontal asymptote next. Here's our function. Horizontal asymptote, we're going to look at the powers of x. On top, you have x to the 0 power. There's no x's there. On bottom, you have a 1. And let's go back and review up here what happens when the degree on bottom is bigger than the degree on top. If the degree on bottom is bigger than the degree on top, you have this scenario. Y equals 0 is going to be your horizontal asymptote. So let's scroll back down. So my horizontal asymptote is y equals 0. That is your x-axis. So let's plot that. And now, hopefully, that makes sense why you didn't have an x-intercept, because it doesn't cross the x-axis. So therefore, there's not going to be any points of intersection there. So we're set up and we're ready to graph this thing. We've got our y-intercept. We can plot maybe a couple more points. We already know down here with this single point kind of what your graph is going to do. It's going to follow this asymptote line. So it's going to look something like this, and that's close enough of a graph for what we need here. However, what happens to the right? Is my graph down here or is it up here? So what I would do is I would find one single point, find some x value over here to plug in, maybe 3. Let's plug in 3 and see what happens. Here's my function. When you find f of 3, you get, let's see, 1 over 3 minus 2 is 1. 1 over 1 is 1. So when you plug in 3, you get 1. So your graph is here. So again, you kind of know that it's going to follow these asymptote lines. So it's going to look something like this. Okay, the next one. Okay, we always start out by factoring. So the top is already factored, x minus 1. The bottom has a common factor of an x squared. Factored out, you're left with an x minus 1. Okay, now this one's going to be a little bit different looking graph. You do have some removable discontinuity there on top and bottom, but your domain, let's start out there. X cannot equal 0 or 1. Plugging in a 0 here would make that x squared equal to 0. It kind of can equal 0 twice because of that x squared. You can think of it like that. So there's your domain. Let's talk about, is that a vertical asymptote or a hole? Since you have removable discontinuity at x equals 1, that's going to be a hole there. So a hole at x equals 1. And actually, you know what? I forgot to put that hole in my last graph. Let's go back to it and go ahead and place that hole in. And that hole was located at 3, x equals 3. So that's going to be right here where I actually plugged in that point. There will be a hole in the graph there at 3, 1. And if you don't remember how to find that hole, once you've removed that discontinuity, then you can plug it in to find out what it's equal to. So, and that's what we're going to do here. Now that we have our discontinuity removed, that removable discontinuity, I can actually plug that 1 in and find out that my hole is going to be located at 1 comma. When you plug that 1 in, you get 1. So I have a hole located right here at 1, 1. Okay. So here again is my new function after discontinuity has been removed. F of x is equal to 1 over x squared. Let's see, x-intercepts, well, first off, vertical asymptotes, the other point of discontinuity, since x can't be 0 or 1, my other discontinuity must be a vertical asymptote, and that's going to be at x equals 0. Let's go ahead and plot that. And there we go. Next up, let's find our x-intercepts and our y-intercepts. To find an x-intercept, again, you plug in 0 for y, so you have 0 equals 1 over x squared, which is not possible. And we already know probably y from the last problem. To find a y-intercept, we plug in 0 for x. So we have y equals 1 over 0, which is also not possible. So you're not going to have any x or y-intercepts. So none and none. And you can already see why you don't have a y-intercept, because you have discontinuity there. X can't be 0. So therefore, next up, let's find our horizontal asymptote. The way that you do that, look at the powers. On top, you have no x's. On bottom, you have 2 x's. If the degree of the bottom is greater than the degree of the top, then y equals 0 is your horizontal asymptote, which again explains why we didn't have an x-intercept. So let's go ahead and plot that horizontal asymptote. Okay, there. So now you have your two asymptote lines. You already know that since your graph is up here, you know exactly what's going to happen. You have this hole here at 1, 1, but your graph on each side of that is going to follow, and that looked bad. It's going to get closer and closer to that asymptote line. I did it again. I don't want it to bounce back up, because you want it to increasingly get closer and closer and closer, but never touch it. So let's try one more time. And that looks a little bit better. And now we've just got to figure out what happens on the other side. What happens when x is -1? So let's go back to my function, which is right here. And you can do a small t-table, and you can plug in a couple of values, -1, -2 maybe. When x is -1, you get 1 over -1 squared, which is actually +1. So -1, +1, which is up here. When x is -2, you get 1, 4. Which is going to be about right here. And you can already see what's going to happen. Again, it's going to follow this line, and then it's going to start following this line. So there's your graph, and you do have that hole in your graph. Number 7. Step number 1, we always factor. The top is difference of squares. Difference of squares will always factor into conjugates. 2x times itself gives you 4x squared. 3 times itself gives you the 9. On bottom, we can factor a 2 out. You're left with x squared minus 1, which is also difference of squares. And to save a step, let's go ahead and x squared minus 1, let's write as x plus 1 and x minus 1. So there's your factored form. Your discontinuity is located at x equals -1 and +1. So that's what x cannot be. X cannot be -1, x cannot be +1. Question is, do you have a hole there, or do you have a vertical asymptote there? Since neither one of those are factors on top, you have no removable discontinuity, then you will have no holes. Both of these points will be vertical asymptotes, or both of these discontinuities. So you'll have a vertical asymptote at x equals -1 and at x equals +1. Let's go ahead and graph those two vertical lines. And there you go. We can go ahead while we're at it, and we can find, it doesn't matter what step or what order you do these in, you can find your horizontal asymptote next if you'd like. To find your horizontal asymptote, you always go back to this and you look at the degrees. The degree of the top is 2, the degree of the bottom is 2. Reminder that anytime the degrees are the same, you simply take your leading coefficients. Y equals, the leading coefficients were 4 and 2. So y equals 2 is going to be your horizontal asymptote. Let's go ahead and plot it. And there you see it. So we now know kind of that's where our graph's going to follow. So what we're going to do now is let's find our x and y intercepts. And you can plug it into either place. To find an x-intercept, we plug in 0 for y. So we have, I'm going to use this factored form over here, 2x plus 3 times 2x minus 3 over whatever's on bottom is equal to 0. And the reason I said whatever's on bottom, it doesn't matter what the bottom is, because the only way for a fraction to equal 0 is if the top is equal to 0. So we're really not concerned about the bottom. So my two x-intercepts will be negative 3/2 and positive 3/2. So I have an x-intercept at negative 1.5 and positive 1.5. So that already tells me over here what my graph's going to do. It's going to kind of come up and it's going to follow those asymptote lines. So there's that portion of my graph. And if you would like to, we can go ahead and graph over here as well. But now the question is, what happens in the middle? So let's go ahead and let's find our y-intercept next. To find a y-intercept, we're going to plug in zeros for all of our x's, and that's going to give me y equals, it's probably going to be easier to plug it in here. This goes to 0, this goes to 0, and you get negative 9 over negative 2, which is 4.5. So my x-intercepts, let's go ahead and write these down, were, I'm going to write it like this, plus and minus 3/2, 0. My y-intercept we just found was 0, 4.5, which is located at 1, 2, 3, 4.5, which is right in here, which still doesn't tell me a lot about my graph. However, you can plug in, -1 or -1, but you can plug in maybe 1/2 and see what happens to your graph. But when you do, what's going to end up happening here is your graph is going to still follow these. It's going to come down, touch there, and then go back up. So there's what your graph's going to look like. So we got our domain. Now let's talk about the range. And a reminder, this point right here was 0, 4.5. So my range goes from negative infinity up to my horizontal asymptote line, which was 2. Did not include that because that was not a point on your graph. Then it started back at 4.5 with a point on the graph, and it went on to positive infinity. So there's all your information. Next one, number 8. Okay, let's factor both top and bottom. The top, we're going to have to use slip and slide. So let me come on down here. X squared minus 14x plus 24. Two sets of parentheses, x and x. Adds multiplies would be a negative 12 and a negative 2. We slip the 3, so now let's divide by it. And the top will factor into x minus 4 times 3x minus 2. The bottom factors into two sets of parentheses, x and x. Adds multiplies would be a negative 4 and a positive 1. Therefore, let's go ahead and take care of our discontinuity. X cannot be 4 and x cannot be negative 1. So our domain x is not equal to 4 or negative 1. Then you can answer the question of, well, what happens at 4 and negative 1? Is it a hole or is it a vertical asymptote? Since x minus 4 is a factor of top and bottom, you have a hole. So there's going to be a hole located at x equals 4. So therefore, the other one, x equals negative 1, since it's not a factor on top and bottom, must be our vertical asymptote. What I like to now do is remove that removable discontinuity, and let's rewrite our function. So our function is now f of x is equal to 3x minus 2 over x plus 1. Now that we have that discontinuity removed, we can actually find out where our hole is actually located. So let's plug in our 4, which before was not allowed, but now here we can plug it in and we can find out where the hole is located. 3 times 4 is 12, minus 2 is 10, over 4 plus 1 is 5. When you plug in 4, you get 2. So therefore, my hole in my graph is going to be located at 4, 2, which you can actually 1, 2, 3, 4, 1, 2. You can draw that hole on your graph. Next up, let's go ahead and find our horizontal asymptote, and you can do it from here. That'll be fine. You're going to find your degrees at the top, degree at the bottom. If the degree on top and bottom are the same as they are here, then you look at your leading coefficients. And your horizontal asymptote is going to be located as y equals 3 over 1, which is the leading coefficient on top and bottom, which is y equals 3. Now let's go ahead and let's plot those horizontal and vertical asymptotes, which are at x equals -1 and y equals 3. And there those are. Next up, you can actually already tell what this part of the graph is going to do down here. It's going to look something like this. However, if you want to find a couple more points just to make it a better looking graph, you can plug those in. So let's make us, let's find us our x-intercepts and y-intercepts first. That's going to help. But find an x-intercept, we plug in 0 for y, so we have 0 equals 3x minus 2 over the bottom. However, again, a fraction equal to 0, the only way a fraction can equal 0 if the top is equal to 0. Solve this gives you x is 2/3. So you have an x-intercept at 2/3 0, which is going to be located about right there. So that gave us a little bit of help with the guide for our graph on the right side. Our y-intercept will also, to find a y-intercept, we plug in 0 for x. So you have y equals 3 times 0 minus 2 on top is -2. 0 plus 1 on bottom is 1, so y is -2. So that's going to be 0, -2, which is located right here. So very easy to graph that portion of our graph now. It's going to look something like this. The only thing is, what does your graph do on the left side of that horizontal or vertical asymptote? So what I would do is plug in a couple of points on the left side just to see where it's going to go. Maybe plug in -2 and -3. When you plug those values in, here's what you get. And I've went ahead and plotted those points as well. So your graph on this side will look something of this nature. Again, follows the horizontal and vertical asymptotes. So there's your graph. You do have to do the range. We've not done it yet. So the only break in your range, it goes from -infinity up to your hole, actually. So we could say from -infinity up to 2. Then it goes from 2 up to the asymptote line, which is located at 3. Union, then it goes from the asymptote line up to positive infinity. So you could write it like that. Or you could just say y does not equal 2 or 3, which is probably going to be the quicker way of saying it. Everything else is on your graph except for 2 and 3 for your range.